Hello everyone and welcome to my channel. Today I'm going to extend our understanding of sp3 hybridization of methane, water and ammonia to other forms of hybridized orbitals. First, we're going to look at the sp2 hybridized orbital. This hybridization is applicable to the head center atom in group 13 of the periodic table. Like for instance, we're going to look at boron, which has 3 electrons in its outer orbital or in its valence shell. So therefore, the hybridization scheme combines the hybridization scheme combines the 2s orbital of boron and the 2p orbitals of the same boron, combines them together in order to form 3 sp2 hybridized orbitals. Just brighten this up. Don't want to make my diagram to be boring. Yep. So that is the purpose of the hybridization process. We have to note that since there are 3 sp2 hybridized orbitals, we have to note that only one of the p orbital in boron will be left unhybridized. In this case, because you will note here that in general we have 3 p orbitals, but in this case here we are combining the 2s orbital and the 2p orbitals. Let's say for example the x and the y. We hybridize these orbitals here and we leave this one left. This one will be left unhybridized. So this is what I'm trying to say in this particular hybridization scheme. So the diagram which I'm going to show next, this diagram here shows the graphical illustration of what we're saying here. So what I'm saying is that the 2s orbital, which is a square, will combine with the 2px and the 2py, and once you're combining them, they will be hybridized to generate the sp2 hybridized orbitals, and these hybridized orbitals are 3 in number. If you note here, we have 3 atomic orbitals being hybridized to form 3 hybridized orbitals. So this is hybridized 1, which is located on the x-axis. The next is located between planes, and the last one is located on the opposite side or in the mirror image side of the other plane. So If we combine these three together in the special geometry on boron, we have three lobes which are 120 degrees apart from each other, and they are all positioned in the XY plane. This sticker note here shows how boron is being transformed from its atomic orbital state into its hybridized orbital state. So once you apply the hybridization on the atomic orbital of boron, because we know that boron has 3 electrons, you fill up the first two, the 2s orbital, then you add 1 electron to the 2p orbital. So by hybridization, you are taking out the 3 orbitals here and leaving one of the p orbital unhybridized. And what results from this case is that 3 atomic orbitals being hybridized to form 3 hybridized orbitals, and this electron here will undergo an excitation and then a spin flip. So in here we have three half-filled orbitals which will be involved in the bonding with 3 hydrogen atoms to form BH3. So for this sp2 hybridization, which corresponds to the trigonoplanar that is being formed in this process here. So trigonoplanar will be formed in this process, and this will be a planar compound in that case, and the angle that will be formed will be 120 degrees between the boron and hydrogen bond. Next is the sp hybridized orbital. This sp hybridized orbital focuses on the group 2 elements, which are the alkaline earth metals. So in here we're going to look at beryllium, which has 2 electrons in its valence shell. Therefore, what we are going to observe is that the 2s orbital of beryllium will be hybridized with the one of the 2p orbitals of beryllium, and by hybridization this yields 2 intermediate sp hybridized orbital. However, we note that 2 of the 2p orbitals would remain unhybridized. In this case, Now this, I'm going to introduce a new sticker here, and this sticker shows the energy diagram before and after hybridization. So in this sticker here, we have before hybridization, beryllium having 2 electrons in the 2s orbital in its atomic state, and when it's being hybridized, what happens is that 2 of the atomic orbitals, which are 2s and one of the 2p orbitals, will be hybridized to form the sp hybridized orbitals, and leaving the remaining 2p orbitals unhybridized. So you note here that the unhybridized electrons will remain at a higher energy level compared to the hybridized orbital, which are in the intermediate state between the 2s orbital and the 2p orbital. And in here we have 2 half-filled orbitals, and these 2 half-filled orbitals will be involved in the bonding between beryllium and another atom. Let's say, for example, chlorine, to form beryllium chloride, and beryllium chloride would result in a sp hybridization that results in a linear electron group geometry, or let me say, geometry, and the angle between the bonds are 180 degree apart. And that is it for the sp hybridized orbital. So the takeaway message for sp hybridized orbitals is that they form linear molecules, and the bond angle between them is 180 degrees apart.